Alright, let's talk about direct sum decompositions. We're continuing into section 23. So here we go. If you have subspaces v1 through vs of a particular vector space v, we say v is the direct sum if any vector in v can be formed from adding together vectors in each of the subspaces. And also we have some sort of independence condition too. In particular, if you've got this sum is equal to that sum, then you can match up the parts of the sum which are coming from each subspace. Like 1 has to go with the 1 prime, 2 with 2 prime, s with s prime. So it's sort of equating coefficients property for the subspaces if they're independent. All right. So if you have independent subspaces whose sum forms the whole space, then it's called a direct sum decomposition. Again, the circles here are linked to number 2. That's not a bad way of characterizing direct sums, but if you wanted to think more about this, you could talk about some sort of isomorphism between the Cartesian product of v1 through vs and nv. There's an isomorphism that's built from just adding together the vectors in the subspaces like this. There's a direct correspondence between a vector space with this structure and the Cartesian product of the subspaces which form that structure. All right, we'll talk more about that some other time, but just a word on that there. Now, lemma 23.5 is, let me just kind of boil it down here. Basically, it just says that the independence condition of equating coefficients can be replaced with the independence condition that if you got this sum equal to 0, then it forces each one of the things coming from each one of the subspaces to be 0. Let's look at the proof. First of all, the lemma really says, this direct sum decomposition, part of that is that the vector space is formed from the sum of the subspaces. So that's kind of beside the point here. There's nothing to prove there. That's automatic from this. All right. And so really all we're asserting is the equivalence of b and 2 here in the definition. All right. So here's the proof of that. It's pretty simple, really. So if you have v as the direct sum of these subspaces, and if you've got this linear combination equal to 0, where each of the v sub i's are taken from the vector of the ith subspace, then you can equate this to the sum of the zeros. In other words, you can look at v1 prime as being 0, v2 prime being 0, vs prime being 0. But then by property 2, we get to equate v1 with v1 prime and so forth and so on. So we get that v1 is 0, v2 is 0, all the way out to vs is equal to 0. Consequently, that gives us property b. Conversely, if we have this linear combination v0 where the v's are taken from each subspaces respectively, right? Well, that implies that v1 is 0 and vs is 0, right? Suppose that's the case, all right? Then consider if you've got v1, vi prime, and vi, each taken from the ith subspace, and you have them such that they're different expansions giving you the same vector, right? So, well, if that's true, then you can rearrange this to get the sum of the differences, v1 minus v1 prime, v2 minus v2 prime, and so forth, equal to 0. And then we can use by b that each one of these must be separately 0, but consequently we have vi is equal to vi prime, hence 2 holds. All right, so we have that freedom with the direct sum decomposition either to look at it in terms of equating coefficients or that a linear combination must be the trivial combination provided, we're taking vectors from each subspace. The next result that we need, all right, is this one, lemma 23.6. So suppose you have a vector space over a field F, and suppose that there exist non-zero transformations E1 through ES, endomorphisms, right, mappings, linear transformations from V to V, such that their sum, the sum of these linear transformations, gives you back the identity transformation, and they're pairwise commuting to 0. All right. Then here's the punchline: EI squared is equal to EI for I equals 1 to S, and V is the direct sum of their ranges. All right. So this E2V is like shorthand for the range of E2. E1V is the range of E1, which is the image of V under E1. All right. All right. So how do you prove this? Well, it's actually pretty fun. If you have this data here, right, calculate EI is equal to EI times composed with 1, right? You should really think of that as, it's not multiplication so much as it is, I mean, I guess it's multiplication in the certain sense, but it's composition to be more concrete. So anyway, so this composed with that, oh sorry, now that I've started, I can't stop. All right. So that composed with that is E1, E2 to the ES, right? But then this with that, this with that, everything is 0, right? Everything is 0 except for the ith with the ith one, right? So I get EI is equal to EI squared. Aha, well that was this condition. And then next, since EI is not equal to 0, it follows that EIV is not equal to 0, okay. And then finally, well, think about this. If V is a vector, then we can rewrite V as 1 operating on V, right? But that's the same as these guys operating on V. Consequently, V is equal to E1V plus E2V plus plus ESV. In other words, V is in the range, the sum of the ranges of these E1 through ES's, all right? So it follows that V is, in fact, the vector space V is the direct, not direct, but it will be direct, but it's not direct yet, is the sum of the ranges of these E1 through ES's, all right? So we still need to show that these are independent subspaces. So to do that, suppose that we've got VI in EI, and that the sum is 0, right? Well, if VI is in EIV, that means that there exists some W sub I in V such that the image under EI of WI is VI, all right? Kind of a gross equation, but you can deal with it. So we have U1 plus U2 plus plus US equal to 0. All right, well that's great. Now if we take that and we operate on that, make sure I'm not out of frame here. If we take that, come on, and we operate that by EI, well that would give us everything 0 except for what? Except for the ith one, right? So this is gonna simplify down to I squared WI. On the other hand, EI eats 0, gives you back 0 again because it's linear transformation. Consequently, we get EI squared WI is equal to 0. But we also know that EI squared is equal to EI. We already just proved that. And so we get that EI WI is equal to 0, but that's VI. But that was arbitrary, so we've just shown that V1, V2 did it all the way out to VS is 0. Follows from this being 0, which suffices to prove the independence of the ranges E1 through ES, right? And by lemma 23.5, we conclude that V is the direct sum decomposition of the EIV. Now this condition that EI squared equal to EI is so important it has a name. It is as follows. A linear transformation that goes from V to V, once more an endomorphism, right, satisfying E squared is equal to E, which is not 0. This is called an idempotent linear transformation. So just to reiterate, what does lemma 23.6 say? It says that if we have a set of pairwise commuting to 0 transformations EI for which the sum yields the identity, then each EI is idempotent, and V is formed by the direct sum of the images of V under these idempotent transformations. So this brings us to the primary decomposition theorem, actually. Let me just kind of give you the lead into that real quick here. First of all, we know that any endomorphism has a minimal polynomial, right? We also know that we can take that polynomial and we can factor it into products of powers of prime polynomials, like that, and by the theory of divisibility, polynomials over field. And we've also shown that the kernel of a transformation which is built from a polynomial of the transformation, the field coefficients, well, these kinds of things are T invariant. All right, if I take T of something like this, I get something like this again. So anyway, just to get to it, the primary decomposition theorem simply asserts that V is formed by the direct sum of the kernels of these prime power polynomials, which are embedded within the minimal polynomial, So I guess this isn't that exciting, but if you understand what this means that you can find a matrix with respect to a basis which reflect. I mean, if you find a basis, you take a first part of your basis from like E with a P1 of T E1, the second part of the basis from like the next one, and so forth. You'd have S different bases, one for each subspace, right? And you can string those together to get a basis for the whole space, like this. And then if you look at the matrix with respect to such a concatenated basis, then the matrix of T will have this block diagonal, very, very simple form, and that will reflect this direct. So block diagonal matrices go hand in hand with these direct sum decompositions, as we'll hopefully be able to see as we go on. All right. That brings us, of course, to the primary decomposition theorem. Here it is. So you have M, product of these prime power polynomials. That's the minimal polynomial. And well, here's what it tells us. There exist polynomials f1 through fs of x such that linear transformations, which are built from evaluating this as a transformation, like EI is built from fi of t from 1 to s, all right? First of all, they're non-zero. And also, the sum of these transformations is the identity. They're pairwise commuting, right? So that lemma we just looked at applies. And in fact, you get each EI, the range of the EI is in fact the kernel of the corresponding prime power in the minimal polynomial evaluated at t. And in fact, V is the direct sum decomposition of these kernels, just like that. All right, so let's get to work on it. Hopefully I won't get stuck this time, we'll see. All right, so the proof goes as follows. First of all, you take the minimal polynomial and you divide by one of the powers in it. All right, so we're going to let M be as it was in the theorem, okay? And so you take M of x and you divide by a particular prime power, right? So if you can kind of visualize that, you take this and you like just get rid of one of the factors, right? That would be the q of whichever one you got rid of. And so intuitively, what's that going to mean? The qi will send everything to 0 except for the part that it doesn't send to 0 anymore, which would be, you know, the ith piece, right? Okay, that's intuition won't be enough here. Let's go on. So if you look at it, Q1, Q2, Qs, if you look at all of them, right, each one is missing one of the prime factors, but they're all missing a different one, right? So there's no common prime factor amongst these. The only common factors are units. Then it follows by the Euclidean algorithm, or I suppose the extended Euclidean algorithm, that there exists a set of polynomials aix such that this linear for which 1 is equal to q1x, a1x plus q2x, a2x plus dot dot. All right. Then you take this, all right, which is given to us by the theory of divisibility over polynomials, and evaluate that at t, and that gets you this identity transformation is equal to this, right? Well, that's really cool. So what we can do is we're just going to define fi to be qix, aix, all right, where the aix is given to us by the extended Euclidean algorithm, which I suppose is not terribly comforting if you don't know it. But I will show you some ad hoc methods we could find the AIs just for kicks after we're done with this proof. Anyway, so define EI to be the fi of t, all right, and I say observe EI is not equal to 0. I guess I think that's clear already, but I think there's a more explicit argument to follow. Anyway, it is clear, of course, that E1 plus E2 ES is equal to 1 is required, right? And also, if I is not equal to j, well then this has the minimal polynomial and then some in it, right? M of x divides this product, all right, great. Which means that if you plug in t, you get 0, right? But on the other hand, EI, EJ, well that's FIT, FJT, which is, by the way, QIT, AI, QJT, AJ, T. you can commute polynomials built from the same transformation. So like, I just put these next to each other, and then well, that's 0, right? So that proves that these are pairwise going to 0. They commute, in fact, to 0. If I did EJ times EI, I'd also get 0. Consequently, well, already we can apply the lemma, right? We've got the things that are needed to imply. I think we have, well, I guess I haven't, suppose I haven't made sure that the transformation's on 0 yet, so I'll hold back just a second here. Okay, so anyway, the next thing we do here is we show that the we're working to show that EIV is in fact the kernel of this transformation. This calculation does part of that, about half of it. So, oops, sorry, let me bring it up here a bit. So here's the start of that. Well, I mean half of it again. So if you look at this, all right, let V be a vector in the vector space. If you look at this, well, that's the same as that because the EI is just QI AI, right? But, well, this is exactly the minimal polynomial with that deleted, divided out, and so like put these two things back together, well, that's the minimal polynomial. Of course, that's 0, and then so this is 0. And then what this actually so EIV, right? When you feed it to this transformation, you get 0. That shows that, of course, EIV is in fact an element of the kernel, right? In other words, the image of the vector space under the EI transformation is a subset of the kernel of the ith prime power in the minimal polynomial. All right, that's half the battle. So we can argue then. Now we need to argue that it's non-zero. Once we have that, then we'll have what we need to apply the lemma. All right. Okay, so here we go. We suppose that it's 0 towards a contradiction. All right. Well, then V is the sum of everything except for this, right? So sum J not equal to I of EIV. I don't need this circle here. That's not needed. Okay, I would white it out. I don't have any white out with me. Oh well. So here it is. Check out what that means. Well, then you'd have QIT acting on V, right? And that would be this, but because we can rewrite V as a sum of everything except for the EIV. And so if you look at that, well then, what is EJ? Well, EJ was QJT, AJT, right? And but these are 0, right? Because that has the minimal polynomial in it. So that goes to 0. So this is 0. But this is 0 for everything in V. That means that this polynomial QIT annihilates the whole vector space. I mean, sends it all to 0. And, well, hey, but this is also a smaller degree polynomial than the minimal polynomial. Well, that's a problem, right? You can't have a smaller degree polynomial, which also, when you evaluate it, the linear transformation gives you back 0. That contradicts the definition, the minimality of the minimal polynomial. So, in fact, this was an absurdity. We can't have that EIV is equal to 0. So EIV is not equal to 0. Consequently, we can apply the lemma. All right, 23.6. All right, so now we're going to consider, suppose you got V in the kernel of the ith prime power, all right? And write V as a linear combination of these, all right, for some appropriate copies Vj in V. And, well, then what? Well, we have that this acting on V, right? So put that in, put that down here. Well, that's fine. That's equal to 0 because we assume that this was in the kernel. Great. But also, because of the T invariance of EI, each one of these is in fact in it's like this one, this thing is in E1V1. I mean, this is in E1V. This is in ESV. All right, because of the T invariance. So it follows we have a sum of vectors, each one being from E1v, E2v, ESV. And by the way, because we satisfied the conditions for the lemma 23.6, we also know that V is a direct sum of these, E1v through ESV, which then shows me that these must separately be vanishing. All right? So we have that this is 0, and everything is separately 0, right? So Pi, Ei, Ej, Vj is 0 for j equals to 1s. Now for I not equal to j, we also can argue that Pit, Ei, Ej, Vj is equal to Pj to the Ej, Ej, Vj equals to 0. The reason for that, in part, is because if I is not equal to j, then these are distinct primes, right? That means that they're relatively prime, there's no common factor, except for a unit. So there exist polynomials a of x and b of x such that you have one is equal to like that. But if you evaluate that at t, that gives me the identity is a of t, ith prime power of t, jth prime power of t, right? If you apply this to Ej, Vj, we get that Ej, Vj is equal to this plus that, but these are 0, right? I'm sorry, I think this is true because of that up there. And then, but that also gives me that, it then follows that, okay, these being 0 in fact implies that this alone is 0 because of this right here, right? So we have, so this is 0 and this is 0 because of the star calculation again. And thus, that's 0, right? So what good does that do me? Well, that tells me that V is equal to E1, V1 plus ESVS is equal to EI, VI. But remember, up here V was what? It was an element of the kernel of this guy, right? And I just showed you that that is actually in the image of the ith transformation, right? In other words, the kernel is a subset of that. But we already proved the other containment, so that serves to prove that the kernel of the ith prime power appearing in the minimal polynomial is in fact the image of the EI under V. Therefore, the kernel of that is equal to that. And that completes the proof of the primary decomposition theorem. I'm going to stop and get a drink of water, and then I'll show you the examples here, okay? Thanks.